Alright, so I have a pin and I've got a piece of string. So imagine that this is just one focus. So I'm going to stretch the string. Oh, the pin fell out. Oh, right, so this is the pin. Right, let me just hold down and then I'm going to draw around it. So draw around. Let's go around here, and then the pin's fallen out again. Right. Look at this. Okay, right. Okay, and then let's put this back there. Right, so you can see that this is a circle, right? So if you've got one focus and then you stretch the string around it and then you draw around it, you get a circle. Now what happens if I have two foci? So let's put two pins in here. Okay, right. And then I stretch around this. So look, if I go around, so you can see that that is an ellipse. Right, let me just put this back in here. So if I put this back, right, so look, if I was to, so can you see that part here? So now that is, let's just say that's C and this is D. C plus D is equal to a constant. If I go around here, C plus D is equal to a constant. If I go around here, that's C plus D. So the distance is D from there to there, and C is the distance from there to there. If I go around again, if I go around here, so this distance here is D, this distance here is C. Let's go around. This distance here is D, this distance there is C. So D plus C is equal to a constant when you go around the circle, when you go around the ellipse.
Let's have a look at the learning outcomes. So for planetary motion, learners should be able to demonstrate and apply their knowledge and understanding of Kepler's three laws of planetary motion. The centripetal force on a planet is provided by the gravitational force between it and the sun. The equation t squared equals 4 pi squared divided by gm times r cubed. And the relationship for Kepler's third law, t squared is proportional to r cubed, applied to systems other than our solar system. Right, let's just have a look at what's in the book. So in the book is talking about eccentricity. Now for a circle, the eccentricity is equal to 0 because there's only one focus for a circle. For a circle, the radius is the same everywhere. That's the definition of a circle. Now the circle is just a special type of ellipse where the major axis is equal to the minor axis in terms of its length. So the semi-major radius is equal to the semi-minor radius. Okay, so for example, at the aphelion, which is the furthest point from the sun, the Earth is 152 million kilometers, and at the perihelion, the closest point to the sun, the distance is 147 million kilometers. So perihelion means the closest point, and the aphelion is the furthest point. Right, so mathematically, the eccentricity E of an ellipse is given by the ratio E is equal to C divided by A. So when A is equal to B, because in the diagram on this slide, 2A is longer than 2B. For a circle, 2A is equal to 2B. So in this case, for a circle, A is equal to B. And then because it's talking about the foci lies on the major axis. So when A is equal to B, C is equal to 0. And the eccentricity is defined as C divided by A. So if C is equal to 0, the eccentricity is equal to 0. Look at this diagram here. Because for a circle there's only one focus, the distance from the center to the focus is 0, therefore the eccentricity is equal to 0. However, what happens when you have two foci? Then you end up with the eccentricity being less than 1 but greater than 0. Right, um, so this is from the book. So from the book, in most cases, the orbits have a low eccentricity. So most planetary orbits are close to 0. The eccentricity of the ellipse is close to 0, as in very low. Pluto, for example, Pluto will have a high eccentricity. This is from the second bullet point for the objectives. So the moon has a gravitational field, and this causes the Earth to be pulled, accelerating towards the moon. Remember, anything that has mass will create a gravitational field, and this pulls the moon towards it. So the Newton's law of gravitation is F is equal to, this is just the magnitude. So the magnitude F is equal to gm1 times m2 divided by r squared. And because of Newton's third law, the moon is pulled towards the Earth, and the Earth is being pulled towards the moon. Now, why is it accelerating? It's accelerating because it's changing direction. And what's causing it to change direction? The gravitational attraction between the Earth and the moon. And then we can equate that to centripetal force. And that gives you Kepler's third law. Right, let's try a question. At its perihelion, a moon comes within 200,000 kilometers of the planet it orbits. At that point, the moon is 300,000 kilometers from the other focus of its orbit, F2. The planet is at focus F1 of the moon's elliptical orbit. How far is the moon from the planet when it is 260,000 kilometers from F2? Have a go at this question and see if you can answer it first. Okay, so I've labeled the diagram F1, F2, C, and D. Now, in the question it says, at its perihelion, a moon comes within 200,000 kilometers of the planet it orbits. So for C, I'm looking at the diagram at the very bottom, the ellipse at the bottom, not at the top, where I've labeled F1, F2. So at the bottom, C is equal to 200,000 kilometers. And then in the question it says, at that point, the moon is 300,000 kilometers from the other focus of its orbit. So in this case, D, which is the distance from the edge of the ellipse on the major axis. So the focus, that's D, and D is 300,000 kilometers. And you know that C plus D is equal to a constant. So in this case, the constant is 500,000 kilometers. The question now says, how far is the moon from the planet when it is 260,000 kilometers from F2? So now, what happens when D is equal to 260,000 kilometers? You know that 260,000 plus C is equal to 500,000 kilometers. So you do 500,000, take away 260,000, that should give you 240,000 kilometers. This is Kepler's second law question. Earth's orbit is slightly elliptical with a semi-major axis of 152 million kilometers and a semi-minor axis of 147 million kilometers. If Earth's period is 365.26 days, what area does an Earth-to-Sun line sweep past in one day? Now, each day, Earth sweeps past an equal-sized area. So we divide the total area by the number of days in a year to find the area swept past in one day. Now we know that the area of a circle is pi r squared, but we know that for a circle the radius is the same throughout the circle. For an ellipse, it's different. For an ellipse, you multiply the two different radii and pi. So the area is equal to pi AB. First calculate A, and then divide by the number of days in a year. So pi times 152 million kilometers times by 147 million kilometers, you end up with 7.02 times 10 to the power of 16 kilometers squared. I've left it in kilometers squared, but it should be in meters squared. And then you divide by 365, but I'll round it up to 365, and then you end up with 1.92 times 10 to the 16 kilometers squared per day. Okay, and then the third question, given that the moon orbits Earth each 27.3 days and that it has an average distance of 3.84 times 10 to the 8 meters from the center of the Earth, calculate the period of an artificial satellite orbiting at an average altitude of 1,500 kilometers above the Earth's surface. Assume the radius of the Earth is 6,371 kilometers. Attempt this question. I'm just going to so attempt this question, and then I'll do the working out. Okay, so you know that t squared is proportional to r cubed. So if you know that something is proportional, you put equals k. So t squared equals k r cubed. First, we need to work out what k is. Now, you can use t squared is equal to 4 pi squared over gm times r cubed. But let's just work out k, because this is a mathematical question about the constant of proportionality. So work out what k is. So find k. So now we can leave it in terms of days. So in this case, t is equal to 27.3. Put r in. You know that r is 3.84 times 10 to the 8. Find out k. Rearrange to find out k. So k is 1.316 times 10 to the minus 23. Once you've worked out k, put it back into the original equation. So now you know that t squared is equal to k r cubed, and you know that value for k. So for the satellite now, because we want to work out what t is, t squared is equal to brackets 1.316 times 10 to the power minus 23 close brackets. Now for this part, you add the radius of the Earth and the altitude. So you end up with 6,371,000 plus 1,500,000, all of that cubed, and then work out t. You end up with 0.08 days, and that should give you 1.92 hours. You could leave it in terms of seconds. So if you look at the box on the right hand side, instead of days, convert t into seconds, and then you end up with 2.358720 million seconds. So then k would now be 9.8256 times 10 to the minus 14. And then you should have t as 6,921.885 seconds. Convert that into hours, you still should get 1.92 hours. Right, have a go at this yourself. Got 3 questions. So number 1, if a small planet were discovered whose orbital period was twice that of the Earth, how many times further from the Sun would that planet be? The definition of orbital period. The term period refers to how long an object takes to complete one cycle of revolution. In particular, the orbital period of a planet, star or planet, is the time it takes to return to the same place in the orbit. And then for question 2, an asteroid has a mean radius of orbit of 4.8 times 10 to the 11 meters. What will its orbital period around the Sun? Take the mass of the Sun as 2 times 10 to the 30 kilograms. Right, for this question, you use t squared equals 4 pi squared divided by gm r cubed. You just put that into the equation, work out what t is. Question 3. Mars has 2 moons, Phobos and Deimos. Deimos has a period of 30 hours, 18 minutes, and the mean distance from the center of Mars of 2.3 times 10 to the 4 kilometers. If the period of Phobos is 7 hours, 39 minutes, what mean distance is it from the center of Mars? So again, you use, for this question, you use t squared is equal to k r cubed. Work out what k is. And then once you've worked out what k is, put it into the original equation. Now you have t, work out r.